Can you see my screen?
Yes, we can see your screen. I'm recording, yeah? Okay.
Okay.
Uh,
Question 1. That's why I be exchangeable Poisson random variables with mean theta. Consider a prior distribution theta follows gamma AB. Then part A is from the posterior distribution theta given y. Then from the title, we can know that the joint PDF is this one, and prior distribution is this one. Then to get the posterior distribution, we just need to multiply them together, and then we can get the answer. It follows gamma a plus summation yi and n plus b distribution. Part B. Show that the posterior mean can be written as a weighted average of the prior mean theta naught and the maximum likelihood estimator theta hat. This part, from the title, we can know the posterior mean is this one, and the prior mean is this one. For the posterior mean, we need to find a way to make the right hand side show theta naught and theta hat. So I just did some rewriting in this form. Then then we can get the result what we need. Okay, that's all.
okay, thank you.
Thank you.
Okay, Mark. Mark Kun,
Hello, doctor.
are you okay?
Can you hear me now?
Oh,
Hello, can
No.
you hear me?
sorry.
Doctor, okay.
You're doing question what? Question 2, are you?
Uh,
Are you okay?
This is my question.
Yes, I think I heard you just now.
can you hear me
Are
now?
you doing? Yes.
I'm Mark.
My question is, yeah, are you doing this question number 2?
But I'm not sharing the screen. I think someone else is sharing the screen. So let me share the screen.
I see. Okay. The one sharing the screen, can you stop sharing?
Oh, okay.
Okay. I think yeah, she forgot.
Okay, so I will share the screen now. Going to, oops, wrong screen. Okay. So, okay. So can you see the workings clearly?
Can you make it bigger? Yeah, thank you. Right.
Okay. So for 1C, we are to find the expectation of a future observation and the variance of the future observation. These were the results from the previous questions. So we have this formula here where the expectation of the future observation can be found with this formula. So so in the inside bracket here, the expectation of z given theta is just the is from the Poisson distribution. So we know that the mean is theta. So this is theta. And from the previous question, just now, we know that expectation of the posterior is the weighted average here. The variance of the future observation can be found using this formula. So looking at the first part of the sum, the variance of Z is also theta, the variance of a Poisson is theta. And then looking at the second part of the sum, the expectation of Z is also theta as well, we did that earlier. So on the second line, the second inequality, so the expression of theta is the mean of the posterior, which is the one that we found earlier, the weighted average, and the variance of theta, um, is going using the formula is just going to be the alpha over the beta squared, right? Which we saw, which is a plus Sn over b plus n squared. So this is the variance.
Okay.
So the here.
Yeah. Oh. Oh, I see. Because why is your? I see. So you actually using the weighted one. Okay.
Yeah,
Right. Okay. Okay.
it's the weighted one. Yeah. So
Oh, okay. Okay. Oh, why it looks so strange? Okay. 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 All right.
so the part D is require us to find the 95% predictive interval from Z. And the question states that the, I believe, sorry, actually this part here, this part here, so this part is given by the question. The distribution is normally distributed with the mean and the variance that we found earlier, right? So for us to use this distribution, we first need to find the values of expectation and the variance, right? And we can use that using the data and the formulas that we shown earlier, right? So the expectation of Z is just this weighted average, which I use back the original one here, which is A plus the sum over B plus N, which is this value, and give us 22.6. The variance is that 22.6 plus the A plus the sum over B plus N squared, which is this, which is 24.1. Okay. So since it's normally distributed, we can find the predictive interval, right? So the standardized value, the standardized Z will be the probability that the standardized Z between negative 1.96 and 1.96 is 0.95. So a bit of algebra here, and we can see that the 95% predictive interval for Z is between 13 and 32. Okay, so that's my solution.
Okay. Okay. A comment. Right. Because the data is because Z is an integer, because it has a Poisson distribution, right? So it's an integer. So you
Okay,
can actually change the value like 32 to 33. So it will be like 13 and 33
I
around there.
see. Understand. All right.
Okay. Okay. Thank you.
Thank
Thank you
you.
very much. Okay. Then I think just now Sinuang reshared her screen.
Oh, sorry, doctor. Can you hear me?
Your voice is very very quiet, very low.
Sorry. Now,
Still low. Right? Everyone else, can you hear her?
oh, doctor. Now,
No, it's still low, I think.
oh, sorry. Wait a minute.
It's okay. All right. I think you maybe you just show your solution.
Okay.
We can try to hear you.
Can you hear my screen? See my.
Yes.
Okay. Sorry, I just thought it was. This question is to prove this formula using the definiteness representation theorem. So we know this, and know the y1 to ym is a first study. So the p theta y1 to ym is a Gauss-theorem distribution, and the ym plus 1 to yn is a second study. So we know that the p ym plus 1 to yn, y1 to ym is a predictive distribution. So using the law of total probability, we have this, and after transformation, we got these formulas. That's my thing.
Okay.
That's
I
my
think
thing.
wait, what was the question?
Question 2.
Okay, right. Okay, I think yeah, I think you need to expand more, but it's okay. It's all right.
Okay, thank you. Thank you, doctor.
Okay. So I think what happened was she did it quite like sort of halfway. It's okay. I will share my screen. Okay. Okay, right. Wait. We have a new one. Okay, right. So for question 2, what happened is actually you have to expand it more. Okay. Right. Right. So because you have to show that, so the originally you have the data, right? So you have this data. So this is a conditional. So you are supposed to open it, change it to the full data. Right. So this is conditional. Okay. So when you have your joint PDF, means that you have joint PDF of y1 up to yn, which is y1 to ym, then ym plus 1 to yn. So you have y1 to yn, and then you have y1 to over y1 to ym. So you have to open the conditional. Okay. So then you have to apply the definitives to the top part. Right. So then you have right, and then the bottom part you just leave it as it is. right? So you have the definity, and this is where actually you can divide, right, the M and N data. Oops. Right, so you have this, right? Okay, wait. Oh, right. So then you can move your prior in front. So this become your likelihood of M, right? Multiply by this. Oh, not enough space, too large. Okay, so this is actually your posterior. Posterior given Y1 to YM. Is okay, so this is actually the answer, right? Wait. Oh yeah, well, it's the other way around, but it's actually the answer that you want. Okay, so the idea here is actually what happens is you have your conditional of the data, right? And then you change it using the definity. Okay, and then because you have the conditional is actually joined for A and B, which is Y1 up to Yn. So you use the definity there. Then you can divide your multiplication of your I, right, to two parts, which is I from 1 to M, and then one from M plus 1 to N. And then with some maneuvering, so what happened here is you move your prior in front, and this actually becomes the posterior of theta given Y1 to Ym, and then multiply by the data. Okay, and this is and okay, so so here, why I use this one, because it's too long to write, right? So actually, your this py I given theta is actually that function, right? Because it's just too long to write, so I just use py I given theta. Okay, so actually you can use theta also, but just use py I given theta. Okay, so this is how you can show that actually your data, conditional data, is actually given can also be equal to your new data multiplied by your old posterior or your current posterior. Okay, meaning that if I were to have Y1 to YM represent data from a first study, then I have a posterior based on Y1 to YM. Then we have a second study, and then we have YM plus 1 to N. Then we can actually update the posterior for the whole data using the all of posterior from the first data as the prior. Okay, so that is that is how we explain. Okay, so do you have any question about this class? Right, well, except for my handwriting, hopefully you can see. Question class? No? No question class? Okay,
Question.
so if there no question. Okay, so if there's no question, then we go to the next question. Stop sharing.
Okay, I'm here.
Okay. All right, you can share your screen now.
Okay. So can you see my screen?
Yes.
Okay. I solved the question 3, which consists of two small problems, A and B.
Sorry, Rangi, are you using your tablet or something?
I use the MacBook.
Laptop, notebook. Oh, okay. Right. Can you make it larger?
Okay.
Okay. Yeah. Thanks. Okay.
I solved question 3, which consists of two small problems, A and B. For question A, it requires us to prove that the sum of the squares of yi minus mu, which is s, is a sufficient statistic for phi. For py, by calculation, the likelihood of the vector y is this expression. We can observe that s is included here. So S is a sufficient statistic. Okay, here we can refer to the factorization theorem to get the conclusion. For problem B, when phi follows to an inverse gamma distribution, let tau be equal to the reciprocal of phi, which requires us to prove that tau follows to a gamma distribution. In this regard, we define the transformation tau equals to q phi equals to the reciprocal phi. Okay. Then p tau is calculated and finally simplified to this expression. Obviously, we can observe that tau follows the gamma distribution. Okay, that's all.
Okay, for question B, right? So again, please state the parameters. So I think the phi has inverse gamma, right? So it should be inverse gamma AB. Then the tau would have a gamma AB also, right? So
yeah.
I think you have to mention the parameter for the distribution.
Okay.
Okay. It's actually inverse gamma AB, and the tau would actually have also a gamma AB. Okay.
Okay.
All right. Thank you.
Thank you.
Then Lema, I think, are you there though? Oh yeah, Lema, you're there. We cannot hear you. Are you talking? I cannot hear your voice. Are you? I cannot hear your voice though. No voice. Really no voice. Everyone else cannot hear him also, right? Oh, him or hear her.
Yeah, I cannot hear so.
Cannot hear also, right? Yeah, we cannot hear you. Why is it? Have no. Okay, if you cannot hear you, then it's okay, right? You can just show. Maybe you can just show your answer. Okay, maybe yeah. Then I have to say it. Yeah, we still cannot hear your voice. The It's okay. Yeah. Okay. Right. Okay. Uh, oh, okay. All right. Okay. I think we can see your answer. Okay, so let me just explain your answer. So for C just now, right, your posterior is inverse gamma, right? So now if you use then you can show that the probability in the question, right? And then you want to find the probability that phi is bigger than 0.255. So actually your tau gamma, you have your tau gamma, I cannot see actually. Then you have your it's gamma 0.5, right? So 1 over phi is actually chi-square 10 degrees of freedom. So you can find the distribution. Oh, I see. You integrate, okay, whatever, but you get your answer, which is probability is 0.049. Okay, right? I mean, you don't have to integrate actually because it's a chi-square, right? You can use the table or you can use the R to get the answer. But it's okay. It's a correct answer, right? So, anyone have question? For question 3? Actually, no. Okay, no, it's okay. All right. So, thank you. Thank you, Lima, even though we cannot hear your voice. It's okay, right? I think you have